In this question, make sure that you go through the first part of the question highlighting the essential details. So first of all, we're looking at a compound, benzaldehyde, and we can see that it's reacting with potassium hydroxide solution. And we're looking at mechanisms and we're trying to deduce some kinetic data. The very first question says calculate the value of the square, so we're getting the square of the concentration of the benzaldehyde. So you simply need to go to your calculator and type in, find out what 0.25 squared is. So you go to your calculator, so that's 0.0625. And in this case, that's 0.25, 0.56, and 1 squared is 1. Then you need to take this data and you need to plot it on the graph. Now the most important thing to notice here, it says label the axes with units. So what do you have to do? Write your answers, done, plot a graph of initial rate of the concentration and label the axes with units. That's what I'm going to do now. There's the units for rate, moles per dm cube per second. Here is your sample paper 2, the physical and organic chemistry. Work through it. It will take you up to 10 pages and the next video will follow. So it's important that when you plot your graph that you've labelled the axes. So this is the concentration of the benzaldehyde. And the units are moles per dm. So you can see here that the units are moles squared, dm to the minus 6. Whenever you do units, notice that there is this forward slash to denote the units. Again, on the initial rate, you'll notice that the units are in moles per dm cube per second. You've been given that in the table previously. The next thing is to notice that all the points, there are no anomalous results and the line passes through all the points, and make sure you use as much of the graph as possible. So from the graph, deduce the order of the reaction. Now when I looked at the marks, when I looked at what a lot of students have done, because they've got a straight line, automatically they assumed it was first order. However, you have plotted a graph of rate equals, the gradient is the rate constant, versus the concentration of benzaldehyde squared. And therefore it must be second order with respect to the concentration of benzaldehyde. Second order. So there's your explanation. So rate is directly proportional to the concentration of benzaldehyde squared. I think this question threw a few people because they noticed the word benzaldehyde and dimerization. However, if you look at the question, there's the reactants, there are the products, and yet in the rate equation we've got this pesky cyanide ion. So therefore, if the cyanide ion is not participating, is not represented in the overall equation, and yet it's in the rate equation, the role of the cyanide must be a catalyst. Explanation does not appear in the overall equation. And yet it appears in the weight equation. So as you can see, the cyanide ion is somehow playing a part in the reaction, so it will be involved in one of the determining steps. This question here is about the destruction of the ozone layer and goes back to your AS chemistry when you were looking at catalysts and halogenoalkanes. And therefore, rather than try and memorise this, it's best to look at the chemistry behind it. So again, as usual, let's highlight and see what the essential details are. So first of all, it's about halogenoalkanes. And it tells us information that we knew from last year, that they're formed in the upper atmosphere, so chlorine atoms in the upper atmosphere when ultraviolet radiation causes the CCl bonds in chlorofluorocarbons to break. Two equations to show how chlorine atoms catalyse the decomposition of ozone. So you know that the chlorine atom by the fact that a chlorine atom has got 7 outer electrons, has got an unpaired electron, and therefore it's a chlorine radical. You also should remember that ozone is an unstable allotrope of dioxygen, or oxygen as the one that we breathe in. And what you need to see is if this particle, this radical, collides with this ozone molecule, the most likely atom it's got to collide with is an oxygen atom. And therefore, if this chlorine collides with this oxygen atom here, you're going to form chlorine joined to an oxygen, you're going to form chlorine oxide. And therefore, the unpaired electron now appears on the oxygen atom. If you then look at what's left over, and cover up chlorine and oxygen, you're going to end up with a dioxygen, or the oxygen that you breathe in. Now, there's lots of scenarios that could happen, but the chlorine oxide is a very reactive intermediate that doesn't appear in the overall equation, and therefore, to get rid of this, if we collide it with yet another, so there's your chlorine oxide radical, collide it with yet another ozone molecule, what's the most likely atom it can collide with? Well, the most likely atom it's going to collide with, so you can see that the oxygen on the chlorine oxide is likely to collide with an oxygen atom on the ozone. So when it does, the most likely atom it can collide with, as I say, is here, and therefore we're going to get a chlorine radical regenerating, and now if you count the number of oxygen atoms, 1, 2, 3, 4, you're going to get a total of 2 oxygen molecules. If you add the two equations together, you'll notice that the chlorine radical appears on both sides, and therefore we can cancel it out. The reactive intermediate also disappears, and therefore the overall equation for this reaction is 2 molecules of ozone breaking down to give 3 molecules of dioxygen, or normal oxygen bonds. Before tackling this next question, remember we're still on haloalkanes. Don't try and answer this part of the question until you're confident that you can do the rest of it, otherwise you'll hazard a guess. So we're looking at the reaction of chloroethane with potassium hydroxide to form ethene. The best thing to do is if you sketch out underneath what's going on. So chloroethane, as we know, is a chlorine atom joined to an ethane molecule. and it's reacting with potassium hydroxide, and as usual I'm going to leave the potassium ion out because it's a spectator ion. As usual, because it's hydroxide, I'm putting a lone pair of electrons on, and we know that it's forming ethene. I'm drawing the crab notation because later on we can spot EZ isomers. Always be thinking outside the box. And obviously if you look here, we've got far too many hydrogens on this side and that side, and then so we will have formed some water and chloride ions. Now, if you remember from your haloalkanes, a hydroxide ion has two main roles. One role is a nucleophile and the other one is as a base. And you can see here that protons certainly have been lost, and therefore it's behaving as a base. And therefore the role of the potassium hydroxide is a base. Now in this reaction, propanol has not taken part. So the propanol hasn't taken part in the reaction. It's not mentioned any rate equations, so the only thing is that chloroethane is not very polar, and potassium hydroxide is obviously soluble in water, and because propanol can hydrogen bond, it must be acting as a solvent. Because this is not really polar, and as you know, ions are very polar, and therefore it might happen that they're both dissolved in the propanol. So again, the next question is a nice easy AS question where we're looking for the reaction between chloroethane and potassium hydroxide. Let's draw the structures again. There's our chloroethane, and we've already ascertained that the potassium hydroxide is a base, and therefore we'll decide what the name of the mechanism is after we've done the mechanism. So it's with hydroxide ions. Don't forget your lone pairs. Don't forget also to put the polarity onto your molecule. So chlorine is slightly more electronegative, and therefore this has an effect. It's carbon pulling electrons away from these little protons. All electrons being sort of pulled towards this side of the molecule. So if the hydroxide ion is attacking protons and behaving as a base, remember it will only attack protons that are adjacent to the carbon atom. So it could attack any of these protons on carbon 2, but it doesn't tend to approach these protons because they're too close to the chlorine. So it's going to go for one of these guys here. So if it does, remember it's going to form a bond with one of the protons. So curly arrow comes from the lone pair to the proton, and if this proton is lost, this carbon here will be without a bond. So in order to compensate for that, what will happen is a pair of electrons will move from the bond that used to bond the hydrogen to the proton to the middle there. Now this carbon here, this one here, would now have 5 groups in effect, and that's impossible. So something has to leave. The most logical atom to go is the chlorine. Again, remember that all electrons flow in exactly the same direction. So the electrons are going from here to here and ultimately to here. None of the arrows are flowing together. So that mechanism, that's behaving as a base. And we notice that the molecule that's formed is an alkene. So we've lost proton and we've lost chlorine. and we formed a double bond here, and we must have formed water because the OH here has picked up a proton. So we form water. Don't forget your water. And therefore a small molecule has been removed, so it's base elimination. The next question is on polymerization, and because oxygen is not involved, it's not a polyamide, it's not a polyester, it's a simple addition polymer. And from last year you should also remember that the repeating units in simple polymers are usually 2. So if I circle here this unit and this unit, it simply keeps repeating itself. So in order to draw the structure of the monomer, you represent the alkene, and there's a fluorine, 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 and a chlorine. Fluorine, fluorine, chlorine, chlorine, and you stick a double bond in. So there's your monomer. This 6-mark question isn't as hard as it looks because it goes back to some very, very, very basic calculations. First of all, there is a chemical analysis, and obviously you've got a percentage of fluorine, chlorine, no hydrogen, it's a chlorofluoroalkane, and therefore we know it must contain carbon and fluorine and chlorine. It's got no hydrogen. They're also telling us the ratio of the isotopes of chlorine, that chlorine 35 is the most abundant, so the ratio there is 3:1, and fluorine in this case has only got one isotope, isotope 19. So mass spectrum is obtained using electron impact ionization, which sort of hints at electron spray ionization and electron impact. And if you remember electron impact ionization, you should remember that in this case electrons are knocked off and you get positively charged ions. So there are 3 molecular ion peaks. So that is telling you the molecular mass. So you've got you can work out the empirical formula because you've got your percentages. You can work out the molecular formula because you've got the relative molecular mass. So all we need to do is to determine the formula of the 3 molecular ions of B, and then explain the ratio of the relative abundances of each of the molecular ion peaks. So what I'm going to do is I'm going to call that number 1. That's the question. So what do I have to do? I've got to do that. 1. I've got to do that. 2. And I've got to show all my working. So 2 questions. So R, T, F, Q. Read the full question. The first bit is easy peasy. So we know that this molecule is a chlorofluoroalkane, so it contains carbon, fluorine, and fluorine, and no hydrogen. We know the mass that would be in 100 grams because we've been given the percentage by mass. So it tells us there is 51.6% fluorine. So if you had 100 grams of the compound, 51.6 grams would be fluorine. We know that there is 32.1% chlorine, and therefore what is left over must be the carbon. So in this case, 32.1 and 51.6, and the mass of carbon all adds up to 100 grams. And therefore that tells me that the mass of carbon must be 16.3 grams. As soon as we've got mass, we're chemists, so we go to our periodic table to find the relative atomic mass, and the relative atomic mass of carbon is 12. Now, if we go to our periodic table and look for the relative atomic mass of chlorine, it's 35.5. And the relative atomic mass of fluorine is 19.0. Make sure that you're recording all of your relative atomic masses to one decimal place. Tell them, because it's saying show your working, you must say that to get the number of moles, or the amount, that equals the mass over the relative atomic mass. Don't just dive straight for your calculator. Show the examiner that you have converted to amount in moles, which is mass over AR. So when you divide 16.3 divided by 12.0, your answer comes out to 1.358. 3 sig figs. Similarly, when you divide 32.1 over 35.5, your number of moles comes out 0.904. Dividing 51.6 by 19.0 comes out at 2.716. Thinking back to AS, how do you get a whole number ratio when you have to divide all by the smallest? Why are you doing this? Tell the examiner to get a whole number ratio. And when you do that, the ratio comes out to 3 carbons, 2 chlorines and 6 fluorines. So what was the smallest number? Well, you divided them all by the smallest, which is this one here. From the molecular ion peaks, we know that the relative formula mass, the MR, is roughly between 220 to 224. Because it was in the molecular ion peaks. And therefore we know that the empirical formula repeated x times equals the molecular formula. And therefore the empirical mass, it follows, repeated x times equals the relative formula mass. So the number of repeating units, the number of times the empirical formula repeats itself, is the MR over the empirical mass. So just to remember that the empirical formula was C2Cl2F6, and we'll repeat that x times, and that will give us the molecular formula. Well, when we add all of these together, it comes to 220, assuming that, of course, you've got 3 carbons, which equals 36, assuming that the chlorine isotopes are chlorine 35 times by 2 is 71, and fluorine times 6. Add all of that together, and that gives us an empirical mass of 220. So empirical mass times by the number of times it repeats itself is equal to the relative formula mass. And therefore, we were told that the relative formula mass is 220, and therefore 220 times x equals 220, and therefore the empirical formula in this case equals the molecular formula. So there's three possible scenarios for our structures. One of them could contain the 2-chlorine-35 isotopes. And 6 fluorines. One of them could contain the chlorine-37 and the chlorine-35. Fluorine. And one of them could contain both of the rarest isotope of chlorine, which is chlorine-37. Don't forget to draw the whole structure. Now don't forget that the molecular ion peaks are caused not by the molecule, but by the fact they've had an electron knocked off. So don't forget the positive charge. Now for the next bit is to look at the ratio of the peaks of these ions, and that was the tricky bit that a lot of you struggled with. So let's explain this word working out. If we remind ourselves and go back to the start of the question, we know that the two isotopes, chlorine-35 and chlorine-37, have respective abundances in the ratio of 3 to 1. So the total abundance is 4, and therefore the number of chlorine molecules, or the proportion of chlorine molecules having a mass of chlorine atoms having a mass of 35 is 3/4. So every 3 out of 4 of them will be at chlorine-35. Now the rarer isotope, chlorine-37, every 1 in every 4 of the chlorine atoms will be chlorine-37. So let's work out the abundance of this molecular ion here. We've got 2 chlorine atoms, each with an abundance of 3/4, and that is why we multiply the two together, because there are 2 chlorine atoms per molecule. Let's look at the molecule again. Each with a mass, 1, 2, 3, each with a mass of 35, and that is why we multiply the abundance twice. So that's 3/4 times 3/4, which is 9/16. The second molecule, this one here, we have 2 chlorine atoms, which is where you get the 2 from, one of which has an abundance 1 in every 4, that's the chlorine-37, and 3 in every 4 is chlorine-35, and that comes out at 6/16. So the ratio is 6/16 of this molecule here, this molecular ion here. So finally, to get the proportion of molecules which contain the rarest isotope, chlorine-37, well, there were 2 of those chlorine atoms in the molecules, that's 1/4 times 1/4, which comes out as 1/16. So again, if you divide through by the smallest, the ratio comes out to 9/16, to 6/16, to 1/16. Divide 3 by 16, so the ratio is 9 to 6 to 1. You divide through by 6/16. It's not been asked for, but if you were asked to sketch the peaks and the MZ, don't forget that on a mass spectrum, There's the mass to charge ratio. There's the abundance. So the ratio is 9 to 6 to 1, where this is C3, Cl2, both isotopes 35, F plus. So that's that isotope there. So the mass to charge ratio is 220. The mass charge ratio of this isotope, and this is the mass to charge ratio of this isotope. Question 3 was asking you, again, this is simple AS isomerism. So you've got an alkane with a molecular formula C5H12. And the best way of doing this, solving this problem, is to construct skeletal formula for C5H12. So you've got the straight chain isomer. So it's got 1, 2, 3, 4, 5. And then you must have the branched isomers. So if we now take a carbon from the end here, take this one off. One, two, three, and you can branch it there. Is there anything else you could do? Well, yes, you could take off this carbon here and branch it yet again. You can't do any more branching, and therefore the number of isomers must be 3, and these are chain isomers. That was some easy peasy AS chemistry. Now let's move on to the next part of the question. The next part of the question asks you to look at the 3-dimensional representation of 2 enantiomers. So immediately we know we're looking at optical isomerism, and they need us to draw the structure. The way I would tackle this is I would draw, first of all, the 2D structure of 2-hydroxypropane nitrile. So that's expecting you to know that a nitrile group is CN. Prop, so it's 3 carbons, 1, 2, 3, and it's got a hydroxy group on carbon 2. By drawing the 2-dimensional structure, you can see at a glance that the asymmetric carbon, the chiral centre, is carbon number 2. So now we go about drawing the 2 enantiomers. Do not forget your mirror plane. Draw 1 enantiomer by starting with a tetrahedral structure. So 2 groups in the same plane, 1 bond coming out at you, so we show a wedge, and the bond behind it we can't see, so we draw as a dotted line. Please practice drawing these. It's like an umbrella that's blown itself inside out. Get some weird and wonderful student drawings of these. So to draw its mirror image, you've got 2 bonds in the same plane, the wedgie bond opposite, and the bond behind it you can't see. Select any group. So there's a hydrogen, so it must be reflected in the mirror there. Get rid of that. There's the nitrile group. I'll stick that there. It doesn't matter where it goes. There's its mirror image. There's the hydroxy group. I'll put it there, and therefore that is reflected there. Make sure the oxygen is bonded to the carbon, not the hydrogen bonded to the carbon. And then we have finally a methyl group. There are your 2 enantiomers. Be careful when you answer the next question how they can be distinguished. You must mention the term plane polarized light. So by pass plane polarized light through a solution of the enantiomers or separate enantiomers The solutions will rotate light in opposite directions. Take care to write in full sentences, but you make sure you use the term plain polarized light. Plain polarized light.